A decision tree is a visual map that shows every possible choice decision node a manager can make, all the chance events that can happen after each choice chance node, and the final results outcome leaf. Decision node drawn as a square, it represents a point where the manager decides what to do, for example, launch a new product or wait. Chance node drawn as a circle, it shows an uncertain event that will occur after the decision, for example, market demand, will be high or low. Terminal node drawn as a triangle or a dot, it records the monetary payoff or utility of that path. Formally, a decision tree is a finite rooted directed acyclic graph T equals open parenthesis V comma E close parenthesis, where each edge E is labeled with a probability P of E if it leaves a chance node, or with a decision alternative if it leaves a decision node. The sum of probabilities of all outgoing edges from any chance node equals 1. The tree is solved by rolling back from the leaves to the root, replacing each chance node with the weighted average of its children, the expected monetary value, and each decision node with the maximum of its children, the optimal choice. An everyday analogy is a choose-your-own-adventure book. Each page decision leads to different story branches, chance, and each ending has a score payoff. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. Explanation: the expected monetary value, EMV, tells you the average profit you would get if you could repeat the same decision many times. Mathematically, for a chance node with k possible outcomes, EMV equals the sum from I equals 1 to k of Pi times Vi, where Pi is the probability of outcome I and Vi is its monetary value. Example: suppose a firm can invest $100,000 in a pilot project. If demand is high, 40% chance, the payoff is $250,000. If demand is medium, 40% chance, the payoff is $120,000. And if demand is low, 20% chance, the payoff is 0. EMV equals 0.4 times 250,000 plus 0.4 times 120,000 plus 0.2 times 0 equals $158,000. Subtract the cost, $100,000, gives net EMV equals $58,000. The expected value of perfect information, EVPI, measures how much you should be willing to pay to learn the future outcome before deciding. EVPI equals EMV with perfect info minus EMV without perfect info. To compute EMV with perfect info, take each possible future state, choose the best decision for that state, multiply by its probability and sum. Continuing the example, if you knew the demand level, you would invest only when demand is high or medium. EMV perfect equals 0.4 times 250,000 minus 100,000 plus 0.4 times 120,000 minus 100,000 plus 0.2 times 0 equals 0.4 times 150,000 plus 0.4 times 20,000 equals $68,000. EVP I equals 68,000 minus 58,000 equals $10,000. So paying up to $10,000 for market research is justified. Assigning probabilities is the bridge between business intuition and quantitative analysis. You can use historical data, expert judgment, or market surveys. When new information arrives, Bayesian updating revises the probabilities. Posterior P of H given E equals P of E given H times P of H divided by P of E. H is a hypothesis. For example, demand will be high, and E is newly observed evidence. For example, a competitor's advertising spend. Prior belief that demand is high equals 30%. You receive a market report saying a new technology is being adopted, which occurs 70% of the time when demand is high and 20% when demand is low. The overall probability of seeing the report equals 0.7 times 0.3 plus 0.2 times 0.7 equals 0.35. Posterior equals 0.7 times 0.3 divided by 0.35 equals 0.6. After the report, the chance of high demand jumps to 60%. This updated probability replaces the original value in the decision tree chance node, altering the EMV calculation. Sensitivity analysis checks how robust a decision is to changes in key inputs. The simplest method is one-way sensitivity, Vary one probability or payoff while holding others constant, then redraw the EMV. A threshold break-even analysis finds the value at which the preferred decision switches. Mathematically set the EMVs of two competing branches equal and solve for the variable. Example in the pilot project, suppose you are unsure about the probability of high demand pH. EMV invest equals pH times 150,000 plus 1 minus pH times 20,000. EMV reject equals 0. Solve EMV invest equals 0. pH times 150,000 plus 1 minus pH times 20,000 equals 0. pH equals negative 20,000 divided by 150,000 minus 20,000 approximately negative 0.15. Impossible. Since EMV is always positive, investment is safe for any realistic pH. If the numbers were tighter, you might find a threshold like pH equals 0.35. Scenario analysis builds separate trees for optimistic base case and pessimistic sets of assumptions, then compares outcomes, helping managers present a range of possible futures to the board. Large trees become unwieldy. Pruning removes branches that cannot be optimal. Two common rules are: Number 1, dominated branch elimination. If a decision branch always yields a lower payoff than another branch regardless of probabilities, drop it. Number 2, roll-up of chance nodes. Replace a chance node with its EMV as soon as all downstream values are known. This reduces the depth of the tree. Computationally, a full binary tree with n decision stages has 2 to the n leaf nodes, so exhaustive evaluation is exponential, big O of 2 to the n. Software packages, for example, at risk in tree age, use memoization and branch and bound techniques to avoid recalculating identical subtrees, bringing practical problem sizes down to 15 to 20 stages on a laptop. For very large strategic problems, analysts often combine a high-level decision tree with Monte Carlo simulation for subcomponents, a hybrid approach. Real options thinking treats strategic choices as financial options, the right but not the obligation to act later. A decision tree can embed 3 classic options. Option to defer, a decision node where you wait for more information, cost of delay is added. Option to expand, after a successful pilot, a branch leads to a larger investment. The later investment is valued like a call option. Option to abandon, a branch that allows you to cut losses, sell an asset if outcomes turn bad. Mathematically, the payoff of an option can be approximated with the Black-Scholes formula or a simple binomial lattice that mirrors the decision tree structure. By assigning a value to flexibility, the EMV of a flexible strategy often exceeds the EMV of a commit now strategy, even if the immediate cash flow looks smaller. Example, a tech firm can launch a minimal viable product MVP for $50,000 now, payoff uncertain. It also has the option to invest an additional $150,000 after 6 months if early sales exceed a threshold. The value of the expansion option is the expected upside of the later investment minus its cost, and this option value is added to the EMV of the MVP branch, making the overall strategic choice more attractive. Explanation: when you pick a modeling tool, ask 3 questions. A, how many uncertain factors are there? B, do you need to capture timing and flexibility? C, how much computational power is available? Decision trees excel when the problem has a clear sequence of decisions and chance events, and when you want to see the logical flow. They are intuitive for managers but can become large quickly. Payoff matrices or decision tables are best for simultaneous choices with a few discrete strategies, for example price versus promotion. They lack a temporal dimension and cannot embed wait and see options. Monte Carlo simulation runs thousands of random scenarios to estimate outcome distributions. It handles many continuous uncertainties but does not directly show the decision logic pathways. You must embed the decision rule outside the simulation. Game theoretic models focus on strategic interaction between rational players, for example entrants versus incumbents. They provide equilibrium concepts, Nash, Stackelberg, but usually assume perfect information and static payoff structures. In practice, an MBA team might first sketch a decision tree, then use Monte Carlo to stress test the probability inputs, and finally apply a game theoretic model if a rival's reaction is critical. The combination leverages each method's strength while compensating for its weakness. Explanation Sample Exam Question 1. Scenario: a pharmaceutical company considers developing a new drug. Developing costs $80 million certain. After Phase 2, there is a 30% chance of success, go to market with profit $250 million. A 50% chance of modest success, profit $120 million, and a 20% chance of failure, profit $0. A market study can be purchased for $5 million before the decision. The study will reveal the true probability of success as either high 70% success or low 10% success with equal prior odds. Tasks. 1. Build a simple decision tree without the study and compute the expected monetary value of develop, now versus do not develop. 2. Perform Bayesian updating after observing a high success report and recompute the expected monetary value. 3. Calculate the expected value of perfect information and state the maximum price the firm should pay for perfect information. A solution template. Step 1. List payoffs, profit minus development cost. Step 2. Expected monetary value equals 0.3 times 250 minus 80 plus 0.5 times 120 minus 80 plus 0.2 times 0 minus 80. Step 3. Expected monetary value of do not develop equals 0. Choose maximum. Step 4. Prior probability high equals 0.5, low equals 0.5. Likelihood of high report given true high equals 0.7, given true low equals 0.1. Posterior probability high given report equals open parenthesis 0.7 times 0.5 close parenthesis divided by open parenthesis 0.7 times 0.5 plus 0.1 times 0.5 close parenthesis equals 0.875. Step 5. Updated expected monetary value equals 0.875 times 250 minus 80 plus 0.125 times 0 minus 80. Step 6. Expected value of perfect information equals perfect information expected monetary value minus expected monetary value without. Perfect information expected monetary value equals 0.3 times 250 minus 80 plus 0.7 times 120 minus 80. Choose best action per state. Compute numeric values. Sample exam question 2. Scenario: a retailer can either open a new store now, B. wait 1 year for market data, or C. do nothing. Opening now costs $2 million and yields profit $5 million if demand is high 40% and $1 million if demand is low 60%. Waiting costs a delay of $0.5 million opportunity cost, and after a market survey the retailer learns the true demand level before deciding. The survey costs $0.2 million and is 100% accurate. Tasks. 1. Construct the decision tree with the weight and survey option. 2. Compute expected monetary values for all 3 strategies. 3. Determine the value of the survey, i.e. the option to wait, and whether it should be purchased. A solution template. Step 1. Draw 3 branches from the root open now, wait, survey, do nothing. Step 2. Expected monetary value open equals 0.4 times open parenthesis 5 minus 2 close parenthesis plus 0.6 times open parenthesis 1 minus 2 close parenthesis equals 0.4 times 3 plus 0.6 times negative 1 equals 1.2 minus 0.6 equals 0.6 million. Step 3. Expected monetary value do nothing equals 0. Step 4. For wait survey subtract survey cost 0.2 and delay cost 0.5 equals 0.7 million upfront. After survey, you choose best action per state. If high demand, open store, profit 5 minus 2 equals 3 million. If low demand, do nothing, 0. Expected profit equals 0.4 times 3 plus 0.6 times 0 equals 1.2 million. Net expected monetary value equals 1.2 minus 0.7 equals 0.5 million. Step 5. Compare expected monetary values. Open now 0.6 million greater than wait survey 0.5 million greater than do nothing 0. So the firm should open now. The survey adds 0.1 million value but costs 0.2 million, so it is not worth purchasing. These templates give students a clear pathway to find payoffs, apply probability weights, roll back the tree, and interpret the results.